Humans have always gazed at the night sky. We have always wondered about those twinkling points of light. What are stars? Could we ever visit them? These questions spark our curiosity. Our closest stellar neighbor beyond our own sun is Alpha Centauri. It's a system of stars. It is incredibly far away from our home, Earth. Reaching it presents an enormous challenge, a challenge that fires up our imagination and drives our scientific quests. We dream of interstellar journeys. Conventional rockets, the kind that take us to our moon or Mars, are far too slow for interstellar travel. If we use them to journey to Alpha Centauri, it would take tens of thousands of years. That's longer than recorded human history. Clearly, we need a new approach. We need something much, much faster. So let's imagine a spaceship, a ship capable of traveling at speeds approaching the speed of light. This is where the real adventure begins. This is where the universe reveals some of its most astonishing secrets. The speed of light is the ultimate speed limit in the cosmos. Light travels at approximately 300,000 kilometers, or about 186,000 miles, every single second. Nothing we know of can travel faster than this cosmic speed limit. When we start talking about moving at a significant fraction of this speed, say 90% or 99% of light speed, strange and wonderful things begin to happen. Our understanding of space and time gets a serious workout. This journey is not just about distance, it's about the very fabric of reality. This kind of travel isn't merely a fantasy pulled from the pages of science fiction novels anymore. While we don't have such ships parked in our spaceports today, the concepts are actively explored by physicists. The implications of near-light speed travel are profound. Such a journey would fundamentally alter our perception of time. It would change how we measure distance. It would reshape our connection to the universe and everything within it. Let's embark on this thought experiment. Let's explore what this means. A brilliant mind reshaped our understanding of the universe in the early 20th century. His name was Albert Einstein. He wasn't just smart, he dared to think differently about the most fundamental things. He proposed that space and time are not separate, independent entities. Instead, they are interwoven. They form a single, four-dimensional fabric called space-time. This was a revolutionary idea. It changed physics forever, and it's key to understanding our journey to Alpha Centauri. One of Einstein's most startling insights, part of his theory of special relativity, is that the speed of light in a vacuum is constant. It's the same for all observers. It doesn't matter how fast you are moving or in what direction. If you measure the speed of light, you will always get the same value. This seems simple, but this simple postulate has incredibly far-reaching consequences. It forces us to rethink our everyday notions of time and space. It leads directly to some very non-intuitive effects. One such consequence is a phenomenon called time dilation. The name might sound a bit technical, but the basic idea is quite straightforward. Time dilation means that time can pass at different rates for different observers. It depends on their relative motion or their position in a gravitational field. For our journey near light speed, we are interested in time dilation due to relative motion. If you move very, very fast, close to the speed of light, time for you will pass slower compared to someone who is stationary or moving slowly. This isn't a mechanical trick with clocks. It's not that the clocks are faulty. Time itself is actually passing more slowly for the fast-moving observer. This has been experimentally verified many times. Tiny particles called muons, created in the upper atmosphere, travel near light speed. Their lifespan is very short, but because of time dilation, they last much longer from our perspective on Earth. They reach the surface when they shouldn't. This is real. This is physics. Let's step aboard our hypothetical spaceship. We'll call it the Chronoship. It's a marvel of future engineering, designed for interstellar voyages. Its mission to travel to the Alpha Centauri star system. To achieve this in a reasonable time frame for the crew, it accelerates to an astonishing speed. Let's say it reaches 99.9% of the speed of light. Inside the Chronoship, for the astronauts on board, everything would feel perfectly normal. There is no sensation of speed once they are cruising. The astronauts would go about their daily routines. They would eat their meals, conduct experiments, sleep and watch movies. The clocks on the ship's walls, their wristwatches, even their own biological clocks, their heartbeats, their aging process would all tick along as usual. From their perspective, a minute is still 60 seconds. An hour is still 60 minutes. They wouldn't feel time stretching or slowing down in any way. Life inside the Chronoship would be, in this sense, ordinary. However, the magic of relativity is happening. While time flows normally for them, relative to an observer back on Earth, Their time is moving much, much more slowly. This is the core of time dilation. If 1 year were to pass for the crew aboard the chronoship, according to their calendars and their experiences, a significantly longer period would have elapsed on Earth. The exact amount depends on how close to light speed they are traveling. The closer they get, the more extreme the time dilation becomes. For instance, at 99.9% the speed of light, the time dilation factor is about 22. This means for every year experienced by the crew, approximately 22 years would pass on Earth. The crew is aging, yes, but at a much slower rate than everyone they left behind. This effect is crucial for making interstellar travel feasible within a human lifetime for the travelers. They are journeying through space, but they are also journeying into Earth's future. It's a one-way ticket to a different era. Meanwhile, back on our home planet, Earth continues its familiar rhythm. People are living their lives. They are watching the skies, perhaps, for news of the chronoship. Mission Control would be tracking the spacecraft's progress. They would be sending and receiving communications, though these signals themselves travel only at light speed, causing significant delays over interstellar distances. But the most profound difference is how time itself is unfolding for Earth compared to the ship. As we discussed, for every single year that the astronauts on the chronoship experience, roughly 22 years might thunder past on Earth. This ratio, known as the Lorentz factor, highlights the stark contrast in the passage of time. So, if the crew perceives their journey to Alpha Centauri taking them, let's say, 5 years of ship time, then for the people on Earth, an entire century and a decade, 110 years, would have gone by. This is a staggering thought to comprehend. Imagine the letters or video messages sent back and forth. The crew sends a message saying, "We've been gone a year." By the time Earth receives it, after a 4.37-year delay for the signal at light speed, and Earth sends a reply, many more years would have passed on Earth. The friends and family the astronauts left behind would age significantly. Children would grow up, have their own children, and perhaps even grandchildren. The world the astronauts knew would be rapidly receding into history. Society itself would not stand still during those 110 Earth years. New technologies would emerge. Cultures would shift. Political landscapes would transform. The Earth awaiting the chronoship's signal of arrival at Alpha Centauri, let alone a potential return journey, would be a vastly different place from the one they departed. The crew are not just space travelers, they become time travelers relative to their home world, catapulted into its distant future. This is the poignant human cost and wonder of such a journey. Section 5 Alpha Centauri beckons, a distant unwavering clock. Our destination, Alpha Centauri, patiently awaits. It is the closest star system to our Sun, located about 4.37 light-years away. This distance means that light, the fastest thing in the universe, takes 4.37 years to travel from Earth to Alpha Centauri or vice versa. It's a vast cosmic gulf. Alpha Centauri consists of 3 stars, Alpha Centauri A, Alpha Centauri B, and the small red dwarf Proxima Centauri, which is actually slightly closer to us. It's a fascinating target for exploration. For Alpha Centauri itself, and for any planets that might orbit its stars, time flows on, much like it does on Earth. The stars evolve at their own ponderous stellar pace. Planets complete their orbits. The universe around the fast-moving chronoship experiences time in what we might call a standard way. There's no special time dilation effect happening at Alpha Centauri just because our ship is heading towards it. The laws of physics operate consistently across the cosmos, but perspective matters. The dramatic time dilation effect is specific to the object moving at relativistic speeds, in this case, our chronoship and its crew. Alpha Centauri is not rushing towards us at near light speed, nor are we, from its perspective, before the ship gets very close, rushing towards it in a way that significantly dilates its time relative to the wider galaxy. So, the clocks at Alpha Centauri, metaphorically speaking, tick in sync with the clocks on Earth, accounting for their relative motion, which is minor compared to the ship's speed. Therefore, when the chronoship finally arrives at Alpha Centauri, the star system itself will have aged roughly the same amount of time as Earth has during the journey. If 110 years passed on Earth, then about 110 years minus the 4.37 years it took for the light confirming Earth's state to reach Alpha Centauri would have passed there too. The profound contrast lies with the crew. They arrive having aged perhaps only 5 years to a destination that has seen over a century pass, just like their homeworld. Section 6, breaking the light barrier, fact, fiction, and father time. So our chronoship can get incredibly close to the speed of light. This allows for these amazing effects of time dilation and, as we'll see, length contraction. But a natural question arises. Can we reach the speed of light itself? Or even more daringly, can we travel faster than light? According to Albert Einstein's theory of special relativity, the answer for any object that has mass, like a spaceship or a human being, is a firm no. You cannot reach the speed of light. There's a fundamental reason for this. As an object with mass accelerates and gets closer and closer to the speed of light, its relativistic mass increases. This means it becomes heavier and heavier, not in terms of more atoms but in terms of its inertia, its resistance to further acceleration. To push it even faster requires more and more energy. To actually reach the speed of light would require an infinite amount of energy. And infinite energy is, well, not available. This cosmic speed limit is not just an arbitrary rule, it's woven into the very fabric of space-time. It's a fundamental constant of nature that shapes how everything in the universe interacts. Think of it as the ultimate speed limit sign posted on the cosmic highway, speed limit C. You can get tantalizingly close, pushing your speedometer to 99.999% of CE, but you can never quite hit that final value if you have mass. Only massless particles like photons, the particles of light, can travel at speed CE. This inability to reach light speed is deeply intertwined with the behavior of time. If, hypothetically, you could reach the speed of light, time as you experience it would effectively stop relative to an outside observer. All moments would become one. This is already a mind-bending concept, but what if, just for the sake of exploration, we pushed the boundaries of known physics and asked, what if something could go faster than light? This is where the line between established science and speculative thought becomes wonderfully blurry. Section 7, Whispers of Yesterday. Could time flow backwards? Now we venture into the fascinating and highly speculative territory of faster-than-light travel and its potential implications for time. It's important to stress that this is beyond our current understanding and technological capabilities. No known object with mass can exceed light speed, but as scientists and curious thinkers, it's part of our nature to ask, what if? What if the universe holds secrets that allow for such a feat, perhaps through exotic physics we haven't discovered yet? Some mathematical frameworks, when pushed to their theoretical limits, hint at bizarre consequences if the light speed barrier were to be broken. One of the most startling suggestions is that time itself might not just stop, but could appear to flow backwards for a faster-than-light object, at least from the perspective of certain observers. Imagine sending a message that arrives before it was transmitted, or a spaceship arriving at its destination before it even departed its origin point. These concepts immediately throw up red flags in the form of paradoxes. The most famous is the grandfather paradox. What if you traveled back in time and prevented your own grandfather from meeting your grandmother? Then you wouldn't be born. But if you weren't born, you couldn't go back in time to cause the change. This creates a logical inconsistency, a breakdown of cause and effect, which is a cornerstone of how we understand the physical world. Scientists are generally uncomfortable with paradoxes, seeking consistent explanations. While the idea of actual backward time travel for macroscopic objects remains firmly in the realm of science fiction for now, exploring these theoretical possibilities is not a waste of time. It helps us probe the limits of our current theories. It forces us to question the fundamental nature of time. Is time an absolute unidirectional flow, like an arrow always flying forward? Or could it be more complex, with loops or even reversals under extreme undiscovered conditions? The universe is under no obligation to make sense to us easily. Section 8, Space-Time Origami, Shortening the Cosmic Mile. Let's return our focus to our intrepid astronauts on the Chronoship, traveling at nearly the speed of light but not exceeding it. We've talked extensively about time dilation, how their time slows down relative to Earth. But there's another equally fascinating relativistic effect that occurs at these incredible speeds. It's called length contraction, sometimes known as Lorentz contraction, and it plays a crucial role in how the crew perceives their journey to Alpha Centauri. From the perspective of the astronauts on board the Chronoship, the universe in their direction of travel actually shrinks. The 4.37 light-year distance to Alpha Centauri, as measured by observers on Earth, would appear significantly shorter to them. This isn't an optical illusion or a trick of perception. According to the theory of relativity, space itself contracts along the direction of motion for a fast-moving observer. The faster they go, the more pronounced the contraction becomes. So, the journey to Alpha Centauri is shortened for the crew in two complementary ways. Firstly, their clocks run slow, time dilation, meaning less time passes for them during the voyage. Secondly, the distance they have to cover, in their own reference frame, is reduced, length contraction. It's as if the universe is performing a kind of space-time origami, folding up the distance to make the trip more manageable from the crew's point of view. This makes interstellar travel seem a little less daunting for those undertaking it. This beautiful interplay between space and time ensures that the speed of light remains constant for all observers. If time slows down for you, and distance also shrinks for you, these effects work together. For the crew, they might calculate they are covering the contracted distance in their dilated time, and the speed they calculate for themselves relative to Alpha Centauri could even seem faster than light, but this is a consequence of their altered measurements of space and time. From Earth's perspective, they never exceed light speed. Section 9. A New Cosmic Dawn, Redefining Our Place in the Universe. Journeys like the one we've imagined to Alpha Centauri, traveling at velocities approaching the speed of light, are still firmly in the domain of future possibilities. We face enormous technological hurdles to build ships capable of such speeds and protecting their crews. However, the very act of contemplating these voyages is immensely valuable. It pushes us to explore the fundamental laws that govern our universe. It expands our cosmic horizons. The concepts of time dilation and length contraction are not just abstract mathematical curiosities, they are real, observable phenomena. Physicists witness these effects daily in particle accelerators, where subatomic particles are propelled to near-light speed. Even the global positioning system in our smartphones and cars has to account for time dilation effects, both due to the speed of the satellites and Earth's gravity, to provide accurate location data. Relativity is part of our everyday technology. Exploring these extreme edges of physics and engineering could one day unlock new discoveries. Perhaps we'll find novel ways to manipulate space-time or new forms of propulsion that we can only dream of today. The universe is a vast laboratory, full of mysteries waiting to be unraveled. Each question we ask, each thought experiment we conduct, like this journey to Alpha Centauri, brings us a little closer to understanding its grandeur and our place within it. If humanity ever achieves interstellar travel at near-light speeds, it would represent a monumental leap. We could potentially become a multi-star species, ensuring our long-term survival and expanding our presence in the galaxy. More than that, our understanding of time, space, and our own existence would be profoundly transformed. The cosmos is beckoning, the stars are calling to us, and it is in our nature to listen, to dream, and ultimately to explore. The journey can